So, good time of the day. Welcome and thank you for joining the Education and Training webinar number 106. This webinar will cover the topic of severe accidents in sodium fast reactors and look into a safety study approach and prevention and mitigation of those accidents by design. Before we start the webinar, a few housekeeping items. Please select the option to listen through your computer for better listening quality, audio quality. If you have any technical difficulties, please head to the Zoom webinar support page. You have the link here and you should find answer to the question you may have. The most important part is, and I will show in a second how to do that you can ask questions during the presentation using the question and answer panel on your screen. And at the end of the webinar, there will be a question and answer session and your answers will be answered by the presenters. After this live webinar, we will share the recording and the presentation of this webinar on the GIF public website in about a week. Tomorrow, you should receive an email with a survey to share your feedback on the webinar and help us improve this series. So if you have the time, please do answer this survey. It's helpful to have your feedback. So to ask a question, you should see at the bottom of your screen a Q&A button that is highlighted at the bottom of this slide. And when you click on it, it will open a window where you can type your question and send it to the panelists. You can do that during the presentation, as I said, and all the questions will be answered at the end of the webinar during the Q&A session. So I would like now to introduce our moderator for today. Dr. Patricia Pavier will moderate the webinar today, and she's the National Technical Director of the Molten Salt Reactor Program of the US Department of Energy at the Office of Nuclear Energy. She's been an active member of the GIF Education and Training Working Group since its inception. She was actually the first chair of this GIF working group, and she is now the webinar lead for the Education and Training Working Group. She has been instrumental in establishing the present series of webinars, and she keeps it flourishing with the energy and enthusiasm she puts in it. So as I said, Dr. Pavier will facilitate the webinar today and the question and answer session at the end. I now give her the floor. Patricia.
Yeah, thank you so much. Good morning, good afternoon, good evening, everyone. I am starting this webinar with a memoriam for Joël Guides. The GIF Education and Training Working Group would like to express its sadness, but also its infinite gratitude to Joël, a fervent supporter of fast neutron reactors with two major French milestones, the Phoenix and Super Phoenix, and his contribution also to the advanced molten salt reactor community. We have captured a little bit of Joël's brilliant scientific and professional legacy through 3 different webinars that you can see. He has been really very enthusiastic and always willing to give a webinar. So thank you, Joël, for your dedication and your joie de vivre. The entire SFR community and MSR community is going to miss you a lot, and all the fast reactor developer and community. So again, thank you very much, Joël, for everything. So let's have our 3 presenters today. I'm very happy to introduce Professor Frédéric Bertrand. He is the research director at the CEA, Commissariat à l'énergie atomique et aux énergies alternatives, senior fellow and a professor at the Institut National des Sciences et Techniques du Nucléaire. He has worked for about 20 years at CEA in safety and conceptual design of innovative nuclear reactor, Gen IV and space reactors. We have also with us Dr. Nathalie Seiler, editorial board member responsible for chapter 5 of this book. She's a research director, a fellow expert at the CEA. She's a thermal hydraulics engineer and a researcher in the field of severe accidents in third and fourth generation nuclear reactor. She has supervised the development of physical simulation tools coupled with advanced statistical tools for assessing the safety of sodium fast reactor under various accident transients. Mr. Shigenobu Kubo, chapter editor of the Japanese SFR project, is the Deputy Director of Fast Reactor Research and Development Department at the Japan Atomic Energy Agency. He has been engaged in sodium-cooled fast reactor development since 1989 in Japan. His specialties are SFR system design, safety design, and related R&Ds. He was involved in the France-Japan ASTRID collaboration as design task leader and severe accident task leader. So without any ado, I'm going to give you the floor. I would like to thank you, the three of us, for participating in this GIF webinar series and cannot wait to hear from you. Thank you so much again.
Thank you, Patricia, for this introduction. And here it's our turn to introduce our book. And first, starting by its objectives, which is to capitalize our knowledge and results concerning ASTRID design and other concept design in relation to severe accident. So most of the work has been done in the development of the ASTRID fourth generator SFR demonstrator in the 2010s years, and as well in collaboration with our Japanese colleagues who brought some insights related to the GSFR, but we will talk about this later on in the book. So this book is dedicated to mitigation of severe accident. It means limiting the consequences in terms of radiological release. And it is a crucial issue for SFR, considering the reactivity potential of this kind of reactor, whose core is highly enriched compared to a light water reactor, for instance. The chemical reactivity of sodium is another issue because we have to prevent a large sodium fire combined with a molten core situation. It would not be reasonably manageable. So that's why, considering what I've said just before, mitigation was considered in the design of first SFR, unlike water reactor, whose design did not take into consideration severe accident since the beginning. So this book represents almost 600 pages. And first of all, the dynamic and historical vision of the severe accident approach in previous projects is presented. Then design elements of ASTRID and GSFR are highlighted in relation with severe accident issues. In the fourth chapter, I will introduce the approach for mitigation strategy and study. And then the fifth chapter presented by Nathalie will be devoted to calculation tools used in the ASTRID project. Then mitigation studies, an overview at least will be presented. And in chapter 7, presented by Nathalie, experimental studies and insights as a support to mitigation, device design will be highlighted. And in chapter 8, Shigenobu will present approaches and studies for GSFR. And this chapter is dedicated into the book to other recent SFR concepts as well. And finally, my two colleagues will present additional R&D needs, starting by how we try to identify what was priority in terms of simulation R&D needs and experimental R&D needs, and then ending words. So this book writing was supervised by 6 chapter editors. 4 of us are from IREN, which is an a CEA institute. IREN stands for Research Institute for Nuclear Systems for Low Carbon Energy Production, and it is located in Cadarache in south of France. The two other chapter editors are Shigenobu Kubo, who was presented just before for the Japanese part of the work, and Bernard Carluec, who was a senior fellow from Framatome and who is now retired, but who brought all the historical vision and the safety approach vision into this book due to its large experience in the Super Phoenix project, among others. Additionally to the chapter editors and book editors, about 30 participants contributed to this book, including JAEA, Framatome, EDF, IREN, that I've mentioned before, ISAS, which is the institute in CEA Saclay. And all of this to say that it is a team work. Let me talk about chapter 2. This is a large one, about 100 pages, more than 100, and starting by introducing the general concept on safety approach for SFR with respect to severe accident, by focusing on European project and Japanese project and other ones as well. Then we introduced the main physical features of a severe accident in a SFR, and among others, the aspect related to core reactivity, related to sodium specificity. And then we provided a historical overview of design options versus severe accidents for prevention, for mitigation, and one of the key points is to mitigate mechanical consequences of a severe accident on the reactor vessel. So let me start with safety specificity of SFR, having in mind the specificity of PWR or BWR, that is better known in general. The main point is that SFR core is not in its most reactive configuration at the nominal operating state. And having said this, it means that if you remove the liquid sodium from the core due to sodium vaporization or due to a gas bubble crossing the core, for instance, you can insert several dollars. And to illustrate this, for the Super Phoenix core, this voiding effect was about $7. If you change the geometry, if you compact the core, and the compaction is a result of core melting, because in the intact geometry you have a volume fraction of the core occupied by the coolant. If you remove the coolant and if you melt the core, you will compact the material, or you will remove the steel cladding, and at the end you have a potential of reactivity of several tens of dollars. And finally, a radial compaction of about 1% of the core in intact geometrical configuration would lead to reactivity insertion exceeding $1. Talking about kinetics, as you perhaps know, you have the delayed neutron fraction, which represents the margin to prompt criticality, and this margin is twice larger for a PWR than for a SFR. Additionally, the neutron lifetime duration is 3 orders of magnitude lower for SFR, and the Doppler reactivity feedback is 3 times lower. All this combined, it means that if you insert a certain amount of reactivity, in the case of a SFR core, the power will increase much more and faster than in a thermal spectrum reactor. Talking about sodium, it is a powerful reductor. It means that it will oxidize. It will be oxidized by air, and it will spontaneously burn into air, and it will react energetically with water by producing hydrogen and pressure wave. And it could react as well with the oxide fuel. In terms of thermohydraulics, it is a so good coolant that it can transfer very easily the change of its temperature to the wall of the vessel, to the structure of the reactor vessel. And we have to be cautious about thermal shocks, thermal fatigue. And since it is more volatile than the fuel of the steel, it can react and it can be vaporized energetically through vapor explosion. However, it has a lot of advantages because in normal operation, we have a large margin up to boiling point. So it means that we do not need to pressurize the reactor. So it means simpler reactors than a pressurized reactor. He provides good heat removal capability since it can be heated to a high temperature. Due to this last delta T, we can use the air as a heat sink additionally to the water. And it has the ability to keep fission products such as iodine and cesium, to trap a large amount of them. And it enables to choose an in-vessel retention strategy to terminate the accident. What is the safety approach for SFR in terms of severe accident? The first pillar is the prevention of severe accident, and it is obtained by improving first the reliability of reactor shutdown systems through 3 levels of shutdown system, generally speaking. That is to say a normal one, a diverse one, and additional one that are passive. And I will talk a little bit more about this later on. You can enhance the inertia of the primary pump, and you can design core in order to have a favorable natural behavior. Natural behavior means the free dynamics of the core without any intervention of systems. You can enhance the reliability of the decay heat removal function. So it's in French, but I will explain. So you can extract the decay heat by the power conversion system, by having a safeguard, an emergency power for the feeding of the steam generator, by cooling directly the steam generator, like in the Phoenix reactor. You can plug an emergency cooling system in the secondary loop, like in Super Phoenix. And like in EFR or ASTRID or Super Phoenix, you can have some direct reactor auxiliary cooling system very close to the core in order to have an obvious hydraulic path and to cool the core and to enhance fluid circulation. And finally, due to sodium good filters and possibility to have a temperature around 500 degrees, you can cool you can remove the decay heat through the reactor pit. The mitigation pillar, you have to assess the possibility to release some mechanical energy and to load the reactor vessel. And this loading occurs when you generate a large amount of thermal energy into the fuel. This is an almost adiabatic process. So you will store the energy into the fuel and you can superheat it and then vaporize it at almost constant volume, but you obtain a high pressure here, like 70 bars, for instance, or you can self-vaporize the fuel, or you can transfer the fuel energy to the sodium that is more volatile, and after you can form a sodium bubble at a higher pressure since it is more volatile. And then, since the reactor is not pressurized, and since you have a cover gas made of argon above the primary sodium, you will expand this bubble and releasing some mechanical work, which is integral of the PDV. And so for the first project, some reactivity insertion ramp were assumed by considering the compaction of two halves of the core. And then for larger core, less pessimistic assumptions were retained, like the analysis of particular scenario, like in the Super Phoenix design. Basically, the severe accident sequence initiating severe accident are unprotected transient. Unprotected means that the shutdown system is postulated to be failed or not efficient enough or to be activated too late if you have a fast reactivity insertion. So, having said this, you can have three basic family reactivity insertion, so-called UTOP, U for unprotected, loss of primary flow, ULOF, and local default accident if you have a flow blockage in a subassembly because the subassembly are encompassed in a shroud. So you can block the subassembly, and this blockage can propagate radially to the totality of the core if you do not take any particular design provision. So the accident progression can be explained and represented like this. You start from nominal condition, then you have the primary phase, and into which the sodium begins to boil in general, or the fuel begins to melt, and the core degradation and the fuel movement are mainly located into the fuel subassembly and are actual. Then you have the transition phase into which those degraded zones are unified or propagate radially if the initiator is local in order to form a large molten pool. And then this is the secondary phase. And at the end, you have the relocation phase and the accident termination. You can make, in a way, the parallel with the PWR terminologies that you probably better know with the early phase and the late phase of the accident. Design options in various projects were the following. After Super Phoenix up to ASTRID, reactor concepts were improved as regard to prevention and mitigation. And additional lines of defense, such as a pump inertia, which help to prevent boiling, have been implemented to prevent severe accident. Or you had hydraulic rod. So the principle is to cover ULOF with this. That is, if you lose the primary flow rate, hydraulic rods are sustained by buoyancy forces, by lift forces, in normal operation. And as soon as you decrease the flow rate, they are inserted passively into the core. The Curie point aim is to cover heating transient, and when the sodium temperature at the core outlet increases, so you lose the magnetic property of a specific compound that leads once again to the shutdown actuation. We design core in order, in the way that they are stable around the nominal operating point. And in order to do this, we can rely on reactivity feedback that we can aggregate into three macroscopic coefficients, K, G, H, and providing that if you increase the core inlet temperature, the K coefficient that is negative will stabilize the situation. If you increase the delta T across the core, the G coefficient, which is negative again, will stabilize the power. And if you increase the power, the H coefficient will stabilize the power again. And the interest of this coefficient is that they are measurable in the reactor directly. And you can compare them with neutron physics calculation. The core is designed to minimize reactivity potential and the void worth effect. Here in the ASTRID core, we added, among other provisions, sodium plenum. And so it means if you have a sodium voiding here, you will enhance the neutron leaks and the power will decrease instead of increasing if you have a positive voiding core. And despite all these safety provisions, you can still have some unmanageable scenario, like in any reactor. And we have to identify this kind of scenario and to implement some design provisions, providing that they are physically impossible or very, very, very unlikely with a high level of confidence, so that we can practically eliminate them by taking some practical design measures. Here are some examples of design provisions regarding mitigation. You have here the Super Phoenix reactor design, and first you have the fuel cladding, then the reactor vessel and the reactor building. And there were some experiments in order to test the robustness of the reactor vessel to mechanical energy release. And in the MARA test, which was a mock-up of the reactor, we can mention a core catcher in order to collect, spread, and keep subcritical the fuel after a severe accident. We can mention some devices aiming at extracting from the core region some fuel in order to reduce the possibility and the severity of power excursion. So I will let Shigenobu talk about this, since it is a Japanese concept, the FIDUS, the so-called FIDUS mitigation device, and he will talk about this in one of the next slides. And here we have the transfer tube, and I will further specify this. But in both situations, the idea is to offer some privileged channels to disperse the fuel from the core region. So let me go into chapter 3. Chapter 3 purpose is to present ASTRID design and GSFR design. So starting with ASTRID, so this is the low void worth core, the so-called CFV core. And so this is an horizontal crosscut of the core. You can see here in white the transfer tube. You can see them here with a vertical crosscut. And so they cross the diagrid, the strong back supporting the core, in order to carry on the fuel and the steel onto the core catcher and to spread them. And here you have 3 of them into the inner core. And here you have some reflector, and you have around the core an inner storage. And what is worth mentioning, and I can go back to this slide, and this is that this core is not homogeneous. So it means that we put here a fertile plate between the two fissile zones in order to push the flux upwards and to enhance this plenum leaks. Here you have an idea of the reactor vessel with the hot plenum and the cold plenum here and the core region. And here the instrumentation and the control rod drive line. Here you have the primary pumps and the heat exchanger and the DHR system into the crossing the slab. And here you have the so-called RRB system. It is a DHR system able to remove the decay heat either in forced convection or in natural circulation. And the so-called RRS system is located in the cold plenum, that is protected from the possible mechanical consequences of a severe accident, in order to have a diverse region, to have those heat exchanger and those systems. And finally, here you have a picture of the sketch of the reactor building with the successive barrier here. And then, of course, you have some gas circuit, cover gas, which is made of argon, and then the barrier made of the reactor building. And here I will let the floor to Shigenobu in order to present GSFR design.
Hello, everybody. My name is Shigenobu Kubo from Ibaraki Prefecture in Japan. Now I'm talking about design overview of JSFR a Japanese sodium fast reactor, which was designed in the first decade of this century. And this is an advanced type, the loop design. And the primary pump and intermediate heat exchanger is separately from the reactor vessel and connecting very short piping, as shown in the central figure. And the aim of this design to meet the goal of the Generation IV reactors, such as safety and reliability, economic competitiveness, and sustainability, and so on. This aim is the same as ASTRID. And we have two types of the out of the power, 750 megawatt electricity for the demonstration type, and 1500 megawatt electricity for the commercial type. Both designs are almost the same, just a difference in output power. And regarding safety, for the reactor shutdown, as same as ASTRID, we have diversified two active reactor shutdown system. And we have also incorporated in design one of the passive system, so-called SASS. This passive reactor shutdown system uses Curie point magnet, CPM. Such a design also incorporated in ASTRID. And regarding mitigation, as Frédéric said, we introduced FAIDUS, FAIDUS, fuel assembly with inner duct structure shown in the left-hand figure. In this concept, we have steel duct inside in each fuel assembly. This is for the molten fuel discharge from the core to prevent severe criticality, which may caused by the massive molten fuel compaction. And our JSFR core uses quite conventional, homogeneous design. But sodium boil worth is limited in certain less than certain value. Reference typical value is less than $6. And instead of this, we introduce this FAIDUS sub-assembly each fuel in the core. And we also have the internal core catcher at the bottom of the reactor vessel, same as ASTRID. And regarding the decay heat removal, we have various types of the systems like ASTRID to prevent core damage as a result of the complete loss of this decay heat removal function. So this is an outline of the JSFR safety design. Thank you.
Thank you, Shigenobu. So let me continue with chapter 4. So this chapter is dedicated to the safety approach regarding severe accident and study methodology implementation. So here, if you can see the arrow of my mouse, we assume a preliminary design that is not satisfactory. And there are two ways to put it in the acceptable region of the farmer space, that is to reduce consequences. And this is the idea of putting some mitigation device. And the other way is to reduce frequency of such detrimental situations. And this can be done by reducing and by enhancing the reliability, by adding some prevention measures if we talk here about severe accident issues. I wanted to focus on the situation into which we are interested here in this book. Those are mainly the mitigation situation. This is the farmer space with the operating condition. Here you decrease the frequency. Here you increase the severity. And prevention situation deals with unmelting core. Mitigation situation deal with molten core. And here you have the practically eliminated situations that I mentioned before that should be in a residual risk domain. And the interesting point is that we did not distinguish the frequency inside this domain because we consider that a so small frequency is very difficult to estimate. So through to this flowchart, you can see that we first realized the pre-design of mitigation devices in relation with core designer. And in order to design this, we first estimated what were the effects to counter, to mitigate the accident effect. That are the thermal energy, the power, the mass relocated, its distribution in the vessel, and so on. Then, in order to opposite mitigation action to this detrimental effect, we imagined some mitigation devices and we designed them on the basis of degraded state. And these degraded states aim was to encompass uncertainties by taking pessimistic scenario consideration, pessimistic state of the reactor. And these degraded states were common and could be branched with upstream evolution of the scenario from the initiator to the degraded state. We checked this. Then we assessed the acceptability of the consequences versus fulfillment versus some design criteria, like the vessel deformation, for instance. If no, we have to review our copy and to propose, to suggest another design. If yes, we check and we verified the design of these mitigation devices by less numerous calculation, but more mechanistic calculation, and starting from the initiating event. And this design verification was made with other tools, but we will have the opportunity to tell more about this. And I forgot, of course, at the end, by verifying the design, we should have a significant margin between the loadings induced by the accident and the limit, the loading limit of the barrier that we considered. And then, if everything is okay, we had a consolidated design. So what were the mitigation options? First, transfer tubes. I mentioned them already. And what was the design evaluation criteria? Since the aim of the transfer tube is to limit the mechanical consequences, one of our acceptability criteria and the judge was the mechanical energy release, depending on the tubes, the number of them, their design, and so on. The reactor vessel take a part, of course, of the mitigation because you have to contain all the molten materials in case of the accident and the sodium. The decay heat exchangers has to remain operational in order to manage the long-term cooling of the core material, and the slab as well, in order to not eject some sodium, some fission product in a too large quantity outside of the reactor vessel. We have another goal that was a non-propagation of the accident toward the inner storage of the core, and that's why we had to choose in-house a meshing that should be in-house refined in order to stop the material radially in case of molten material propagation. And then the core catcher should ensure subcriticality of the fuel, cooling, and in-vessel retention. Here, it is an example. Here is an example of degraded states considered for calculating the thermal erosion of the core catcher. I will talk about this one because it was the more demanding. So here, we instead of having 3 tubes open, we consider that only one is open and that we have to relocate all the inner core through this tube. So it means that you have a discharge, a material discharge, that is 3 times longer than if we had considered the discharge through these 3 tubes. And the length of the discharge is directly related to the thermal erosion, to the depth of the thermal erosion onto the core catcher. So I will let the floor to Nathalie.
So hi, everybody. So in order to follow the design and the safety approach presented by Frédéric just before, we need calculation tool. And so the chapter 5 is devoted to this, the description of these tools, and the study are presented in the chapter 6 next to this description. So this chapter, in fact, is divided into several parts. First of all, we described the study methodology, in fact, what kind of tool we have to use for what kind of estimation at which phase of the project. I will describe that just later on. And we have just 3 kind of tools. So I will speak about estimators, physico-statistical tool, and mechanistic tool. For each of them, we describe in this book the main characteristics, the main features, the modeling assumption, and sometimes the solve equation when needed and when it's important. And also we have some insight about numerical method and so on. Of course, we do not, we couldn't put everything inside this book, but we can find a lot of references in order to get insight on all of these tools. And what is important also to highlight is that in this book, in fact, you have an overview of the validation performed on this simulation tool, because we cannot use simulation tool without being sure that they are predictive, and that we are in the good domain of use. So we need validation on experimental data and also on other simulation results, and sometimes we mention some benchmark. The R&D perspective are in the chapter 9. So now about the methodology to use this kind of tool. In fact, we incorporate the safety consideration during the reactor, the courses of the reactor design. So for each phases of this work about the design, we use different tools. At the beginning, of this project, we are in the phase 1. This is we have a preliminary design, and at that time, the major development are still possible. So what we use is to have like an order of magnitude to see what is important or what is not. We use some order of magnitude estimates based on safety criteria estimators in order to identify the strengths and the weakness of each design option. And we select the main option in light of the safety consideration. So this is at the beginning. And then in phase 2, when the design is a little bit advanced, we have fewer possibilities to make changes. So at that time, what is important is to be sure that we forget anything. So we have to take into account all the aspects. I mean, the initial condition of an accident, or maybe some uncertainties on the design and so on. So we need to perform a numerous calculation to study the variability of the result of interest. So Frédéric spoke about, for example, the mechanical load on the vessel. That is a result of interest for the safety. And for that, we developed and we use fast physical scientific calculation tools coupled with advanced statistics to take into account the uncertainties on models and also on initial condition and on the design. So this is a family of tools, physico-statistical, we call that physico-statistical. And in fact, as of course, they are validated on experimental data and so on. So, and at the end, in the phase 3, we have the finalized design, and we have to be sure that it is validated in regards to the safety. So we have no further evolution, and at that time we can use highly validated scientific calculation tool, including at that time all the physical phenomena. I will speak a little bit about that in the next slide. But these tools are required very long CPU time, so that's why we cannot perform a lot of transient. We cannot simulate a lot of transient with them. So they are called mechanistic tool. And on the right side of this slide, at the bottom, I can underline what I said. In fact, this is the course of the transient versus the time, and what we are looking at, it's the output, the result of interest, for example, the mechanical energy. So by using a physico-statistical tool, we get a lot of transient. And this is the red cloud that you see. So we have various scenarios depending on the design option and depending on the uncertainties. And so at the end, we perform a mechanistic calculation also with one of these transients. But the goal at the end is to take everything into account and to check that the margin to the criterion is still okay. So few words about the mechanistic. You're not. Sorry, it's mechanistic tool. So I will not go into detail, but in the book you have information about how we calculate neutronics for the initial state or for the various steady state which are degraded. And we need thermophysical data for our transient because the chlorium are different properties. You know that it's very difficult to get properties of chlorium at such high temperature and different composition of chlorium. So we use also tool for thermochemical chemistry. What is important is that for the transient accident, we consider this calculation scheme, which link one tool, which is SAS, which is used for the primary phase, already discussed by Frédéric. In this phase, the degradation only occurs inside the subassembly. So we can consider multi 1D model with a neutronic point kinetics. And in this tool, we have a good description of the thermomechanics inside the pin and so on. And then when we have the switch to the transition phase, and the secondary phase with the development of a large merged pool of chlorium, we have to make a transition to the Simmer tool, which is a Eulerian 3D kinetic and multi-component. So as you can notice on this slide, it gathers a lot of physics. You have thermohydraulics, you have structural evaluation, so thermomechanics, you have a 3D neutronics. So it's a very detailed, physically detailed tool. But what is important also to notice is the tricky transition from multi 1D representation to overall 3D representation of the core. In this, in some time, we can have some instabilities. When you have done this calculation by the chaining of these two tools, you can get the result of the Simmer tool at the end and couple them to the Europlexus or Autodyne tools which simulates the fast dynamics for the vessel deformation, because we are already said that it is an important point for the safety. But we can also couple our results. I mean, what is the state of the degraded core, what is the temperature, the pressure, the fission product, and so on, to the contain LMR tool for the containment, pressurization, and release of fission product calculation, which is also, as you know, a safety criterion. A few words about the other family of tools, the physico-statistical tool. So, as you understand, in this tool, they are to be very fast. So only the phenomena which are relevant to the accident sequence, I mean, either USAF, ULOF, or UTOP, already presented by Frédéric. So loss of flow or power, transient over power, or subassembly faults. So for each of these kind of family, we have one tool, which the required physics. This physics is derived from a PERT, so a physical phenomena identification ranking table. So we know what are the main phenomena, and so we develop the physical model according that this phenomena. So they are very fast, but they remain predictive, and we check that by their validation against experiment. So in CAA, we have a family, as you can have a look at that on the right side. So we have 3 tools for each of the main sequence of accident, and we have tool for the degraded state, for the relocalization through the transfer tube, or devoted to the debris bed cooling, or as already explained, to the calculation of the to the bubble expansion and the mechanical load on the vessel. JAEA has also such a tool, which is called SuperCOP-D, and which is also devoted to debris bed. Last point is that we can combine all these tools to obtain a complete transient, and we did that.
Okay, so let's see now what kind of results we could obtain with these tools. So starting from natural behavior of the core, mitigation strategy, and addressing various accident families. I will provide some examples of the design of mitigation devices, but you have more, of course, in the book. Other examples of degraded state studies and scenario studies. So this is a huge chapter, again, about 100 pages. And so what is a mitigation device purpose? So it results from the mitigation strategy already explained in chapter 4. We observed that in most configurations that we investigated for transition and secondary phases of ULOF, because I should mention that for ULOF in low void worth core, we cannot have a power excursion in the primary phase of ULOF. But we addressed as well primary phase of UTOP, into which you can have, of course, power excursion during this primary phase. So these preliminary studies had shown that mechanical consequences by fuel expansion were rather low, and by FCI, by fuel coolant interactions, so. But in some particular very unfavorable cases, we observed that we could have a larger storage of calorific energy in the core. That's why we wanted to implement some mitigation devices to limit the amount of fissile material into the core, and to try to have a sort of control in the accident course, and to orientate the material relocation, and to drive them onto the core catcher in order to succeed the in-vessel retention. So here you have some studies starting from a core degraded state, and here, following the arrow of the mouse, you have some simmer calculation at steady power, which was the nominal power. So we adopted this calculation strategy in order to go faster. And you can see these studies was aimed to study the impact of the number of transfer tube. And at the end, we adopted 18 plus 3. So the 3 inner ones enables to actuate the relocation early in the transient, and the 18 following tubes enables to relocate in-house. If you add some tubes, the tubes are not saturated with the material flow rate. You are limited by the molten material that you generate into the core. So this was the optimum. We've made some parametrical studies with the number, the location of the tubes, their cross-section, the upper shielding zerometry, and so on. We investigated with the fast-running Marina tool as well the efficiency of the opening of the tools in terms of reactivity, because in the simmer calculation, here you have not the neutronic module. And so we varied the initial reactivity, the initial material temperature and power. And here you can have this kind of result. And when you get back to negative reactivity, it means that you ejected the material or that you drained them across the tubes. Another example, here, this is the verification of the efficiency starting from the initiating event. And here you have some simmer calculation with a focus made on the stage after the tube opening. And as you can see here, this is the power evolution in brown, and very fast, the power, the fission power is cancelled due to material extraction. And we can see as well that in 15 seconds, we can extract about 30 or 40% of the fuel from the core region. Here, we try to assess the efficiency of the transfer tube against the mechanical energy with more sophisticated tools. I mean, simmer coupled with Europlexus, which is a fast dynamic tool with a fluid structure interaction. And here you can see the bubble at the beginning, and here the growth of the bubble with the closing of the argon region here in red. And then after the end of this closing, you can start to push on the vessel and possibly to deform it. What we observed is that the mechanical energy to this bubble expansion with transfer tube was equal to 0 or negligible. But without this transfer tube, we can have an amount of energy of the order of magnitude of 100 megajoules. This energy stays rather small since it did not challenge the vessel up to it was remaining well below the design energy of the vessel. So what is to take away for these studies is that severe accident studies have confirmed the expected good natural behavior of the CFV core during the primary phase, in particular in case of ULEV. This is a point I mentioned just before. And this was confirmed through mechanistic studies with simmer and through parametric studies and physical statistical studies with fast-running tools. Second point, material relocation devices have been designed in order to cope with a wide range of scenarios. This is a degraded state approach, and we investigated a large domain of adjustable design parameter and to reach the core design, including the tubes. Their efficiency to mitigate secondary excursion has been preliminarily shown. And finally, we verified that we had design margin taking into account scenario variability and uncertainties, both for the transfer tube and the core catcher. I will not go deeper into this because it was explained by my colleague already before. Let's talk about experiments now with Nathalie.
I will present this part on the behalf of Christophe Journeau, my colleague. So this part is devoted to the experimental support study for the mitigation device that we have introduced inside this core. Because as already, of course, we have a lot of existing experimental database before the start of this project, and we remind them at the beginning of the chapter. But you understand that as we have specific features inside this core, like the transfer tube and core catcher and so on, the phenomena are not the same, and the range of parameters, velocity and so on, so Reynolds number and so on, so are not the same. So we need more data to validate our tool and our prediction in such domain of physics. So in this chapter, we present the tests which were in support to the study of ASTRID and of the GSFR. So the chapter is divided into two parts. So one devoted to the out of pile test. So I will describe some of them, and the in pile test. And the conclusion, there are some lessons from from what we gain and the remaining needs. Regarding the out of pile test, we have various subjects, as you can notice. So more detail are in the book. There are some detail about tests about thermochemistry, dealing with the interaction of B4C, steel, and U2. As I already said, as we have introduced in the core transfer tube, we have new phenomena, so new issue. One of them is related to the fact that we will have a large jet, or large, some centimeters of diameter jet of corium through the core which impinge on the core catcher. So we will have a fragmentation of the jet inside the sodium. So there are also some relocation of corium, as you have seen in the Fedius tube in the GSFR. So all these phenomena needs validation, and the melt test have been performed for that. There are also some the eagle of core test carried out in Kazakhstan for this issue. Regarding the heat transfer during this fragmentation, a special test is under construction at CEA. This is a cellular test, which the goal of this test is to have a good knowledge of this heat transfer between the corium droplets and the sodium regarding all the boiling issue, and especially the film boiling. As already said, we have a jet which can be fragmented or not, which will impinge on the core catcher. So this will lead to ablation, and we have to be sure that to ensure the integrity of the core catcher. So we need data and study about this impingement. The GMEC test carried out in Germany have been done for that. There are all steel jet, as you can see on the right side, on a steel block, and to have a view or what happens, and to have more a better understanding of the phenomenology, we also mentioned the Han Solo test, which is in water over the impingement of the water jet on a block of ice. And finally, for the thermohydraulics of the pool of corium on the core catcher, the tests have been performed in KIT and still under realization in the live experiment and are part of the European project like SFR Smart and SFR Simple. So the in-pile experiment, there are two programs carried out in the IGR reactor in Kazakhstan, one managed by JAEA, so the Eagle test. The goal is to validate the prediction of the Simmer code, so the model in the Simmer code for all the phases in which the corium is located in the transfer or outside in the transfer like Fadus tube or outside the core. So different tests have been performed to look at different phenomena, like you can see the discharge of the molten fuel through the inner duct, so the Fadus that we have already presented, or the fragmentation of the relocated materials, or the coolability of the core residual fuel by the sodium reentry. So a lot of issues have been addressed in this test. And regarding the second one, which is a SAIGA test, and which is currently under preparation and managed by CEA, the goal is to validate the opening of the transfer tube. As you can notice at the bottom of the slide, the test section has three parts, one representing the transfer tube, and two other different sub-assembly, one hot and one cold. And the goal is to see, the aim of this test is to see if we will have no trouble to open this transfer tube and to enable the corium to flow through it to the core catcher. So the test duration is very short, as you can see, and we also have an innovative instrumentation in order to follow what the variable of interest for the validation of the tool of Simmer. So one remaining slide about the lesson from this test. What we can say is that all the experimental results are used to validate the tool, so the physico-statistical, but also the mechanism tool, both, and the thermohydraulic database. So these are the tests from the past which have been used for the validation, but so we have our macroscopic code or local code, or we have also performed simulation with very local and precise tool like direct numerical simulation for the thermohydraulic of the corium pool, and we validate this simulation on, as already said, the test performed in the live experiment about the thermohydraulic on the core catcher. What we can say also is that all or part of our mitigation measure that we have put in our design come from some idea or some insight from these previous tests. Like, for example, the transfer tube were inspired for the relocation observed in the Cabri and Scarabée test, as well as by lesson from the more recent Eagle experiment. And so I have already speak about the GMEC and the Han Solo test. And the conclusion, it contributes to the understanding of the phenomena. We need to understand them to model them. And so all these tests, helps to understand and model, for example, the jet ablation and the fragmentation by the entrainment of the and vaporization of the liquid sodium. We use X-ray visualization to catch what happens and then to be able to model them and simulate them.
Okay, so let's move on to chapter 8, Shigenobu.
Yes, Shigenobu Kubo speaking again. And chapter 8 is a small one about severe action to mitigation approach and studies for JSFR and other recent SFRs. Recent SFR means here is the BN1200 and FBR1 and 2 in India. but these two is just a result of the open literature survey. So here is the point is here about the JSFR safety study. So the various measures are incorporated in the design to avoid severe leak criticality and to achieve in-vessel retention. So the design objective is to avoid severe leak criticality and to achieve in-vessel retention here. So we make evaluation of each countermeasure of accident phases as shown here. Initiating phase. So this is a homogeneous core. So the slight positive sodium boil was have. So the slight power excursion may happen, but our objective here is to prevent prompt criticality. So if such result we can get about the SAS4A calculation here. And after that, early discharge phase. Here is we rely on the efficiency of the molten fuel discharge through the molten fuel discharge duct, so-called faders, as we already explained. So thanks to these devices, the core reactivity significantly reduced, as shown in the left-hand hand side graph. The red line shows the reactivity change with Feder's case. After the molten fuel discharge, reactivity significantly change, power decreases at the level of the decay heat. And after that, molten relocation phase, core is already reached to the subcritical state, but still some part of the degraded fuel is remain inside reactor core region. So the molten fuel relocation we need to reach a final cooling state. So in order to this, we introduce some of the design of the controlled guide tube CRGT to discharge such a degraded fuel through such duct structure. And finally, heat removal phase in the so the most part of the degraded core debris are located on the core catcher. So we evaluated cooling capability around this core catcher and also inside the reactor vessel. Maybe that's all I wanted to say here. Thank you. So please go ahead.
Thank you. So chapter 9 related to R&D needs. So we already mentioned the PRT exercise selected to prioritize, and we will provide one slide on R&D needs in simulation and one slide in experimentation. And I let the floor to Shigenobu to explain how we built this PRT exercise.
Yes, so in order to identify the further research and development needs, we perform collaboratively the analysis of the PIRT, phenomena identification and ranking tables. So this study carried out by the CEA, JAEA, MFPR, and Framatome experts. And the subject of their study is UROF, UTOP, and USAF. And at first, we summarize the event sequences by using the generic event trees. So this event trees are very simple, but such simplification is very, very useful to discuss and common item among the expert. So, so we summarize such generic event trees. One example is shown in the next slides. And after that, we identify the quantitative figure of merits. Example shown in the left-hand table. And this table is organized two kinds. as shown in the right-hand figure, sword and shield, or loadings or a barrier. So sword means the loadings which might generate impact on the barriers. And shield or barrier means barriers against radioactive material release, which there's two kinds, barrier against mechanical consequence and barrier against thermal consequences. So this figure will merit organized in this shape. And each item from number 1 to number 15, we break down more in detail, quantitative manner. And based on that, we discuss about the importance on the impact of the consequence, and also the knowledge level, sufficiently or poor or unknown or something like that. The other, so the French and Japanese experts made both on every of such detailed figure of merit. As a result, we identify some of the important items for which needs further research and development. Please, next one. So the left-hand side shows one of the example of the generic European tree. And left-hand hand side list shows the major part of the identified R&D items. Regarding Europe, actually relocation or compaction of fuel, opening of DCS MTT, material transfer within DCS MTT, and so on. These items, this study was conducted for the ASTRID design. So this item is mainly due to the unique design of ASTRID, such as CFB core. In case of CFB core, the volume sodium boil loss is very low. So even the core damage happen, the primary phase conditions a little bit different from the conventional ones. So in this case, actual relocation phenomenon, the compaction of fuel is a little bit different from the existing database. And for UTOP, so the CFB core has no upper blanket. And so the fuel discharge after fuel failure also impact on such a different design. So we identify these items as a result of our study. Okay, next please.
Okay, so here in chapter 9, several words on R&D identified. So for mechanistic best estimate simulation under the name of SIMR5, and also to unify the modeling presented before by Nathalie in a single platform. Regarding experiments, so we need a further test to be performed in terms of in-pile for CFV-like pins, because they differ from those today in Scarabi, thermochemistry, thermophysical properties, and prototypical corium-sodium interaction to support the development of our mechanistic vapor explosion code, SCONE. To conclude, because I don't want to be too behind schedule, so what we can keep in mind is that in former project at the beginning of SFR, severe accident approach, we used envelope approach of mechanical energy. Since Superphoenix, we verify the design with a representative single scenario. But the drawback of this is that we are scenario dependent, so we can forget some scenario, we can miss some uncertainties, and but a core catcher was there already. In EFR, the reliability of automatic reactor shutdown was improved to attempt to exclude the large-scale core melting. But at the end, the ad hoc safety club advised to study it anyway. For ASTRID, we enhanced prevention through passive system in core mitigation device for mitigation, and we designed the core catcher with a top-down approach, including degraded state methodology. And we considered all sequence families, which is a new thing in the approach. So a few words, ASTRID, to remain it, is an integrated reactor with a gas conversion system, CFV core, hydraulic, Curie point, and the mitigation were already mentioned here. So I will let the floor to Shigenobu to talk about the Japanese approach and design.
Yes, regarding JSFR, design measure is prevention by passive means and mitigation aiming at to avoid severe criticality. And JSL design specification is summarized here. And JSFR design, unfortunately, terminated. But now, in Japan, we launch a new SFR project. Conceptual design of the demonstration type of pool type SFR design. And this severe accident prevention and mitigation will be applied in the new project also. Thank you.
Okay, regarding simulation tool, we use static tools for preliminary design, fast computational tools to supporting the design of mitigation device, and mechanistic tools for verification. So ASTRID CFV core exhibited a non-energetic behavior. We have a preliminary design of transfer tubes for highly unfavorable cases and for guiding material relocation. And we investigated the transport of fission products towards the upper part of the reactor, FCI and core catcher, but those items are to be investigated with a greater depth. And finally, experimental studies are completed or are ongoing through integral, in-pile, out-of-pile, and the Saga test. So ending words, this book summarizes the work carried out as a team in a stimulating context, national and international. Following the decision to postpone ASTRID, progress had been made in mitigation and physics, but further R&D is still required. And it will continue within, among others, the French-Japan framework collaboration through the development of the Japanese demo prototype. The authors wish to share their experience, successes, but also difficulties. And if we could help future generation, even a little bit in their new projects, our objective would be reached. Thank you for your attention, and sorry to be perhaps a little bit too long for this presentation.
Thank you. Thank you to the three of you for this very dense and interesting presentation. I assume I'm not the only one being really happy it has been recorded, because there's a lot of knowledge in it, and probably it needs to be gone through several times to get all of it. Quickly, before we move to the maybe short Q&A session, a few updates on upcoming webinars. If I manage to get the next slide on. So, yes, so there's 3 webinars that are already planned and upcoming. One in December, early December, on nuclear energy advanced modeling and simulation tools to support the development of advanced reactor systems. One in January that will cover the history of nuclear reactors development, and one in February on the approach to waste characterization and the use of SynRock technology for advanced fuel cycles. On the next slide, and I'll pass that quickly, but those are instructions for those of you who might have trouble finding the recordings and the presentation of the webinars on the GIF public website. So you should go under events and resources at the top of the website And then this will lead you to all the categories of resources, and you pick webinars, and there either you click on the here that is in capital letters to get a full list in a table of the past webinars, or you can filter on this webinar page by year or by topic of webinars, and this will give you access to all the webinars covering this year or this topic. And with that, I would like to thank again our presenters for the presentation, and give the floor to Patricia if there is time to take 1 or 2 questions maybe.
Yes, I see 3 questions. The first one, could safety be enhanced by the use of nitride fuel with nitrogen 15? The fuel would be high density, thus there may be reduced need for the core size.
So the nitride fuel, the core size, you mean? Well,
yes,
and
could safety be enhanced by the use of nitride fuel? And this would decrease the need for the core size.
Okay, so we investigated some issue like this at CA, and we compared in particular metal fuel with oxide fuel, but we also compared some nitride fuel, but I cannot answer in general terms on this issue. Nitride fuel is a refractory fuel. It has a good thermal conductivity. So in this instance, in case of fuel off, you will minimize the positive effect of Doppler. But we have to analyze what happens in case of top. What are the gas release? Because when you heat nitrate fuel, you have a lot of gaseous desorption. And so it is a large issue, and we cannot. This book is really written for oxide fuel, clearly.
Yes. Second question: where can I buy this book?
You can buy it on the web by clicking the name of the author and of the book on the Elsevier site. It's online.
Okay, very good. The last one sounds like Japan's final SFR design, pool, loop, and fuel type is determined, and a new relevant project has begun. Am I getting that correctly? So is it correct?
Yes, you are correct. So now we are select the pool type SFR for the conceptual design for the demonstration reactor. And now we are studying about the fuel type selection. We have 2 options. First one is oxide fuel, second one is a metallic fuel. And now our conceptual design and related R&D actually starting from the last year. Now we have 5 years program, and now we are undergoing.
Okay, that's very encouraging. So we have a very limited time, and I don't see other questions. But for the participants, you have access to the email address on the Meet Your Presenter slides. So please feel free to contact them separately or together. Again, the book is accessible on the Elsevier website. You just need to click the title and the name of the authors, and it should appear. I would like really to thank the 3 of you, Frédéric, Nathalie, Shigenobu, for a very, very dense and very informative webinar. Like Alexei said, we may need to listen again to it, and that's the beauty of this GIF webinar series. Everything is recorded and archived on the GIF portal. So again, Frédéric, Nathalie, Shigenobu, thank you very much. I wish everyone a very good day or a very good evening. And thank you, Alexei, again for your support. As always, it's very appreciated.
Bye-bye. So, thank you.
Welcome.
Okay, merci.
It's a
Bye-bye,
pleasure,
everyone.
was for us.
Have a good
Bye-bye.
evening. Thank you. Bye-bye.